In most languages, we usually have something called a dictionary. A dictionary can store a collection of data like arrays, but instead of accessing them with an index, you can access them with keys that are associated with each value. They are also called maps because it basically maps keys to values. Some basic operations for the dictionary is inserting a value, which we can do like this, or retrieving a value, which can be done like this. This is going to return the value associated with its key. The idea is that you can store values that can be easily retrieved with a key. An example would be counting the number of times a character appears in a word. If you had the word apple, then the dictionary key value pairs would be this: A with 1, P with 2, L with 1, and E with 1. If we store these key value pairs in the dictionary, we can easily look up how many times a character appeared in the word apple. Today, we are going to be learning one of the implementations of the dictionary using a data structure called hash tables. Dictionaries are also commonly implemented using binary search trees, but today we'll be learning about hash tables and how they work. A hash table is a data structure used to store key value pairs. And the great thing about hash tables is that it allows us to insert, delete, and look up values in all of one time on average. We're going to start to implement a hash table using data structures we already know. First, we'll build something simple. Let's imagine that you tracked how many times you pressed the number keys on your phone. For example, this would mean that you press the button 1 13 times. So you essentially have the keypad numbers as the keys from 0 to 9. And the number of times each key was pressed will be the value. Our solution would be to use an array of size 10 and store the counts in this array in the position corresponding to the keys. So our array would look like this. And we can just use the index as our keys to access the counts like so. This is great because you can get the value of your keys in all of one time, since random access in an array can be done in constant time. Okay, let's change the problem now. I don't want to limit myself to just keys from 0 to 9. I want to be able to store a wider range of keys, like 15 or 100. How would I implement this? This is where hashing comes in. Hashing means converting a number to another, and in our case, we want to be able to hash a key of any number to turn it into one of these 10 numbers. To do that, we need a hash function. A hash function will take any number and spit out a number between 0 and 9 inclusively. What function can do that? The answer is modulo. We can have our hash function be defined like so, which means we're going to mod the number by 10 so that we get the remainder, which is going to be in between 0 and 9. And we'll use the output of that hash function and use it as the index of our array of size 10. Here's a little example. We initialize our array with nothing in it. If we want to store the key 16 with value 5, we would be storing it in index 6 because 16 mod 10 is 6. And next, we want to store the key 154 with value 2. We would be storing it in index 4. Now, you might already see the problem here. What happens if we store the key 14 or 24 or 34? Isn't that spot already taken by the key 154? We can increase the size of our array and change our hash function to mod by something bigger, but there will always be numbers that will collide as long as our array has a fixed size. This is what we call a collision. Many keys can map to the same integer with our hash function. We actually have multiple strategies for collisions like chaining, open addressing, probe sequence, cuckoo hashing, but we'll look at chaining today because it's the simplest. Let's forget about the values for now and just focus on storing the keys. Fun fact, a dictionary without values and only keys is often called a set, which is an ADT that stores unique keys and you're able to retrieve them quickly and see if your set contains a certain key. Okay, So what do we do when we have a collision? So far, we have an array of size 10 and a hash function which is just mod 10. So what if each slot in the array stores a linked list of multiple keys that have the same output through the hash function? So 14, 24, and 154 would be in the same linked list, which is at the index 4 of the table array. We usually call this a bucket. So each slot in the array stores a bucket containing 0 or more keys. So in terms of implementation, the array will contain addresses pointing to the head of the linked list of the respective slot. And then each node within the linked list will be the individual keys we've inserted into our hash map. Here's an example. We will insert the key 46. We will put 46 in the hash function and get the hash code, which is 6. We create a new linked list node and insert it into the bucket as the head. The pointer stored in index 6 needs to point to the head, so we need to update that as well. This also works in the same way if the bucket is empty. We just need to add a new node as the head. And we can keep on adding keys to the hash table like this. So what's the runtime for insert, search, and delete? Insert takes O of 1 because hashing the key, going to the array index, and then inserting at the front of the list are all O of 1 operations. Search will be O of 1 plus the size of the bucket, or length of the linked list, because you'll be able to hash your key and access the pointer to the linked list in O of 1 time, but you'll still have to search the linked list to find your original key, and that depends on the size of your linked list. Delete is also O of 1 plus size of the bucket because you'll have to search the bucket, then delete the linked list node. Deleting the linked list node is an O of 1 operation, as we saw in the linked list module. So now the question is, what is the size of the bucket? If we assume that the outputs from the hash function are uniform, and we hashed n keys, and we have m slots, then we'll have n divided by m keys per bucket on average. So if we inserted 50 keys in our hash table that has an underlying array of 10 slots, then each linked list on average should have 5 keys in them. So that means delete and search on average has a time complexity of O of 1 plus n divided by m. Two things to think about here. The assumption that the hashing is uniform depends on how good your hash function is. In most languages, they use sophisticated hash functions to make sure that the output is as uniform as possible. Also, when is it worth it to increase the size of our underlying array? It's obvious that we're going to start losing the benefit of a hash table if there are too many keys but very little slots. In O of 1 plus n divided by m, if n increases by a lot and we don't increase m, then it eventually becomes a linear time complexity. To fix that, we do something called rehashing, which is similar to a dynamic array where we increase the size of our array for new elements. Rehashing will create a new underlying hash table, a new hash function, and reinsert all the items in the new table. Rehashing costs O of big M plus n, but it doesn't happen that often, so we can ignore this term when amortizing overall operations. One final question is, what about storing the values in addition to the keys? Remember when we learned about node augmentation, we'd had a dic node or dictionary node, which looked like this? If we look into one of the nodes in the bucket, you'll see that it has the key, the value associated with that key, and the pointer to the next node. So each node, instead of only storing the key, you now have the key and the value. Another question you might ask is, what if we want keys that are strings instead of integers? Well, one possible way is to look at every character in the string, convert them into integers using ASCII, add them together, and then mod them. Pretty cool, right? All right, so that's it for hash tables, and I will see you in the next one.